Hey everyone, in this video we're going to talk about gears in general and specifically types of gears and nomenclature. This is the first video that is part of a lecture series on mechanical design 2. So we're going to start this video just by looking at the different types of gears and introducing the different types of gears. There are 4 different types of gears, being spur, helical, and then we'll look at the other 2 in a second. The spur gears and helical gears, their particularity is that they have parallel shafts. The other 2 types of gears are bevel gears and worm gears. Bevel gears have the particularity that they have intersecting shafts. As you can see, the shafts intersect through the middle and they're at 90 degrees from each other. And the worm gear is a special type of gear that looks like a screw basically and rotates a circular gear within that screw type. So I'm just going to write down bevel and worm here so that we have the reference. And what we're going to do in this specific chapter, on gears general, is we're going to study different things about the gears. And what we want to study is the purpose of each gear and why they're used, a little bit about the geometry of the gears, then a little bit about force transmission of the gears and forces transmitted through the gear trains. And finally, a kinematic analysis and kinematic understanding of what is happening. And we'll talk all about that throughout the video series on this chapter. So moving forward, we want to go a little bit more into depth on each type of gear because we did a quick description of what's happening, but we actually want to go a little bit more in depth as to what is happening and how everything is happening. So to start with, we have spur gears. So spur gears typically have what we call parallel teeth to axis of rotation. So they're very simple teeth, very simple design with straight teeth, essentially a typical gear that you would see with straight teeth. And they transmit motion. So what they do is you can have a series of spur gears put together. And as you can see, they transmit motion from one side to the next. Now, the one thing that's important is that you can see that it transmits the motion clockwise, then counterclockwise, and clockwise again. So every time there's a connection, it changes the direction of rotation. It's by far the simplest design because it does have straight teeth, and therefore we use it to develop kinematic relations. So it's going to be used to develop all the relations that we need to know, and all of the calculations that we're going to do are going to be based on spur gears, and then there will be correction factors for other gears if needed. The next type of gear that we're going to analyze is a helical gear. Helical gears, as their names suggest, their teeth are essentially in a helix shape. So they are shaped with a certain angle. And then the advantage of this, and we'll go a lot more into detail on this later on, but the advantage is that they are quieter. And you can see that they also rotate in counter directions. So if one is going clockwise, the other one is counterclockwise. But being quieter essentially is due to the fact that they have gradual tooth engagement. So when 2 gears come together, the teeth engage gradually as opposed to immediately in a flat design. So that's the big advantage of helical gears. Obviously, helical gears are more expensive, so that's why there is a downside to it as well. Finally, going to bevel gears, and then we'll go to worm gears after. But bevel gears, the teeth are formed on conical surfaces. So if you look back at the diagram above, you'll see that they're created on conical surfaces. And the one thing that's important here is that this is really, a bevel gear is used to change direction of rotation. So if we have a rotation in a certain plane and we want to change that rotation, we can change that rotation by having 2 axes at different angles and essentially moving something by 90 degrees. So I'll show it really quick on this diagram below. So you can see that essentially the 2 shafts would be off by 90 degrees, and you can connect those 2 shafts. So you can rotate 2 shafts that are intersecting, but you can change the direction. The last one is worm gear, and worm gear is a type of gear that is non-intersecting and non-parallel. So that's great because we have no intersection between the shafts, which is helpful for us. and in some cases is used for some applications, which we'll talk about later. This is typically like a screw type design where you have a screw type and then you have a bevel gear, or you have, sorry, not a bevel gear, you have a straight spur gear or a helical gear working with that. So the next thing we want to talk about is nomenclature. So for nomenclature, what we want to do is we're going to take this diagram that is shown below. So I'm going to copy over a diagram here so that we have access to it. So it's figure 13.5 in your handout and in your book. And essentially this gives you all the different naming conventions that we have for the gear. And there's some information in your textbook on all the different numbers and all the different things that you have to know on a gear tooth, but we're going to start with the pitch circle. So the pitch circle is the theoretical circle where calculations are based. So this is essentially the starting point when we start calculating things for our geometry as well as for our kinematic analysis. So going from there, we can see that the pitch circle on our diagram is this dotted line that we have on the whole diagram that I'm highlighting right now. And it goes all around the gear. So the gear is a full circle, and this pitch circle goes all around the gear, but it's not on the bottom of the gear, and it's also not on the top or the top land of the gear as shown above. So it's not on the bottom land or on the top land. It's a circle that's used for geometry. And if we have two mating gears together, typically those two mating gears have pitch circles that are tangent to each other. So I'll write it down really quick, but essentially they have pitch circles that are mating with each other, which means that when you're designing a gear system in terms of theory, or you just want to design two intersecting gears, you know that they will be intersecting where the pitch circles are tangent to each other. And that's how geometrically they would be calculated. So the diameter of a gear is not calculated by the top of the gear or the bottom of the gear. It's calculated by the diameter of the pitch circle, essentially. And we'll talk about that a little bit later. So I'm drawing right now a gear that would be intersecting with this other gear train. And in green, you can see that I'm essentially drawing the circular or the pitch circle for another gear. And you can see that the pitch circles would be tangent to each other and touch each other when the two gears are intersecting at that point. So that's a little bit of how that works. And we'll go a little more into detail on that once we start doing problems and start looking at examples as well. So another thing that we need to know about nomenclature is that typically small gears are drawn as a small gear. Then we have big gears as well. So the small gears are usually called pinions, and the big gear is called the gear. So between the two, we have small and big gear, and usually the small gear is just named a pinion. So whenever we refer to the pinion, it's usually the smaller gear of the two. The other thing that we need to learn is that whenever there's three gears put together, the middle gear is kind of there just to change the direction of the gears. And that one is called an idler gear. And an idler gear essentially just transmits forces from the pinion to the gear. And why we use an idler gear is if we want to have the pinion and gear rotate in the same direction, or if we need more space between where we are transmitting the force from the pinion to the gear, or vice versa. So I'm just copying over the diagram again so that we have a clear version of the diagram to be able to describe the next concepts. So the next concept that we're going to go over is circular pitch. And this circular pitch is a distance within the pitch circle. And I'll highlight it above, but I'll write first what it is. But it's usually given by lowercase p. Okay, so it's going to be a little bit confusing because there's a lowercase p and an uppercase p in this class. But just know that lowercase p is your circular pitch. And you'll use that as the distance from one tooth to another along the pitch circle. So it's along the pitch circle. It's basically a repeating distance between one tooth and another. So if we actually draw it out, we can see on our diagram we have circular pitch highlighted already, and I'm going to highlight it in red here so that you can see where it is exactly. Okay, so it's just that distance between the 2 points. The next thing we're going to write out is diametral pitch, which is a capital P. So this is going to be very, very important as well. And try not to confuse the capital P and the lowercase p. I'll provide a formula sheet later on as well that you'll see, but essentially the capital P is the ratio of teeth to pitch diameter, and pitch diameter being the pitch circle diameter. Okay, so P is essentially N, or capital N, which is the number of teeth, divided by the lowercase d, which is diameter. And in US units, it would be essentially in teeth per inch. And diametral pitch is a very, very important metric that we're going to be using throughout, and it's a metric that gear designers use all the time. And I'm just showing the diameter of the pitch circle so that we don't get confused. Now, in SI units, we also have a concept similar to diametral pitch, but of course, things are different between US units and SI units. And in SI units, they use a module, which is lowercase m is equal to diameter, or the pitch diameter, divided by the number of teeth. So it's essentially the opposite of diametral pitch. So it's essentially the exact opposite. So instead of n over d, it's d over n. And the pitch diameter is now in millimeters and not in inches. So the numbers will be different. But you can use either or as part of your analysis, but usually we'll try and stick with diametral pitch, except in some problems with SI units, we'll also do with module. So a few more things. I just copied the diagram again. A is equal to addendum, so lowercase a is equal to the addendum. Lowercase b is the dedendum, and essentially the addendum and dedendum are the addition above the pitch circle and the deduction under the pitch circle of the tooth. So the core of the tooth being addendum and dedendum. And then we can say that h sub t, or the whole depth, or h total essentially, is equal to a plus b. And we can rearrange that equation to say that a, for example, is equal to ht minus b. So if we know the addendum, we can find the dedendum from the whole depth of the tooth. And one more thing that we have to look at is lowercase c, which is a clearance. So you'll see above there's a clearance. It's a little distance at the bottom of the tooth where the fillet radius is placed. And that clearance is important in terms of understanding that really is not part of the tooth. It's the part between, or the merging between the bottom land and the tooth itself. Next thing we can write is, based on our equations and our analysis, we can write that lowercase p, which is pitch diameter, is equal to pi d over n. Okay, and that's the case geometrically, that it is equal to pi d over n because we have a certain number of teeth, and pi d would be your whole circumference. So it's the circumference divided by the teeth. Now, from there, we can also write that because of that, the definition of P is equal to pi over capital P, which is diametral pitch. And in US units, we can then rearrange the equation to say P times P is equal to pi. And in SI units, we can do the same thing. We can show that the pitch diameter is equal to pi times the module. So that concludes this first video. In the next video, we'll talk about some more stuff and we'll continue from here.